I'm going to do some more distortion implementation from the same paper that we looked at Monday. I'm going to do a tube distortion this time. Let's make a new file. We're just going to call this tube. Don't need any of that nonsense. And let's see here, process block. Let's go grab that. What we got, it's called modules, tube. Good. All right. And we can take kind of the same stuff from here. Like let's just take the whole thing. All right, tube, drive smoothers. Yep, don't need this though. Process block, sure. Set drive, sure. But we don't need these two. And we don't need these for now. I guess we are going to use something similar, but one thing at a time. So I will show you the pages from that Will Pirkle addendum. And this one's even easier because he has actual code. He also gives you kind of an overview of the signal flow. So it's got this clipper compressor. It's got this DC integrator. It's got a nonlinear wave shaper, low shelf, DC blocking filter, this high filter, and some amplification and stuff. But that's all, that's all pretty standard. Some of the stuff like I implemented this already just to test this out. Though I don't think the low shelf is even necessary. It seems fine. Also, in his code, he doesn't necessarily use the lossy integrator thing, so just skipped over that, and I mean, it seems fine. Let's just go over to what it's supposed to look like. He also has this. It kind of shows you the natural compression that the tube gives. Oh, and that's something I didn't think to check in plugin doctor. Well, after we implement it, let's check that too to see if it matches up. So where is our oscilloscope view? Here we go. This is what we're looking for. This is the typical tube shape right here. So let's just dive in. It's only really two methods and then a couple of filtering things. So we've got this valve grid conduction and then the actual valve emulation. And then after we do this tube, there's some stuff about it that I like and I think we can reuse to make an overdrive that sounds really good. So yeah, let's get us a nice conduction. And we also process, I'm just gonna call it process tube. Okay, awesome. We need some variables in these, the input and a threshold. Okay. So let's do const float xn const float thresh. And the good thing is that Will Pirkle already found the best values for each of these. We'll do a little optimization after. We'll measure the performance and stuff, but I'm just going to do the if statement first. We do something, and then else we return the input delta. All right, so let's do that. Xn minus thresh, I think it said. Then we'll say clip delta. F max, yeah, okay. Equal to SDD F max. And then we got this compression factor thing. Let me grab that. Const float. And this right here, a tiny little optimization we can do is we don't actually need to calculate this in the sample loop. It is just an addition, but why do it? Static const expr float. I'm just gonna call it I don't even remember what it was called. I'm just gonna say compression term. And then we could drop it in right here. Let's also make sure we're calling stdexp. Oh, yeah, okay. Right there. Return compression factor times xn. And that takes care of the compression part of the tube in this diagram up here. Let's see where we at. This, the clipper compressor. All right, let's do the actual tube part. Now this one's long and it's got a bunch of if statements. And I actually already tried it out and I tried to optimize it with that mask pattern and it actually made it slower. So I guess whenever there's a bunch of if branches, it's actually faster to just do them instead of making this crazy long equation. All right, valve emulation. We need xn. We need drive. We need the threshold. We also need variable DC offset, which if I remember isn't actually really used, but I'm going to put it in there anyway. And then we need clip positive and clip negative. Okay. All right. Start. Simple. All right. So that is the offset. And I guess we don't need it to be const. And let's make this a float. Okay. I'm going to do the skeleton of the if first. So in the first one, xn is greater than the clip positive. We do something. Else, we do something else. Oh, this one's easy. All right. So yn is equal to that. Clip positive. And this one, cool. Okay. This one uses, there is a page with a table of a bunch of different wave shapers, and the arraya is the first one, and it works really well for any kind of like soft squared off shape. This is just called thresh. Now this is, let's see, positive, positive, thresh, thresh, thresh. And then whenever you copy and paste from a PDF, it does this cool thing where the dashes aren't actually a minus sign. Okay, yn. Oh, we just need these to be floats. All right. And then in this positive part, we just do yn equal to xn. And then the bottom portion uses a different wave shaper. So it's going to be similar to this, except for the negative, right? So if it's xn less than clip negative, yn, yep, yn equal to clip negative, else the other wave shaper, just a tan, pretty simple. Okay, clip negative. And I like curly braces in all my if statements. Clean this up a little bit. Okay, that should be good. And then we return yn, which is our wave shaped signal. Okay, and we're good. Now, the only other thing that's absolutely necessary for the shape to be correct is the DC filters. So let's do that. All right, we're going to have an array of Linkwitz-Riley filters because they're just so simple to set up and use. 2 of them for 2 channels. DC filters. How about that? Go up here and set them up and prepare. Filter.prepare, of course. Always need to do that first. We need to set the type, Linkwitz-Riley filter type, and these are going to be high passes. We're going to set the cutoff. 10 hertz ought to be good. Let's take a look at the signal flow just to make sure we're going to do it correctly. We've got our drive, then the conduction, then the offset, which we don't actually even really need, and then the valve emulation, then the DC. Yeah, that's good. Okay. Const float drive is equal to get next value. So we're going to say not const. Xn times equal our drive to actually drive it. Then we're going to say Xn is equal to, I already forgot what it's called, process conduction. Okay, there we go. All right. So the thresh, he gives values for 1.5, and that the threshold for the compression. All right, so that's 1.5, and then we're going to say Xn is equal to process 2. Okay, so Xn, we're already driving it, so I'm not going to add saturation. So I'm just going to pass in 1 for now. We can obviously do whatever we want with that, but I think it's good the way it is. And then we have the clip points for negative and positive, which he gives as 4 for positive and negative 1.5 for negative. And that lines up to some measurements he took in the voltage range. So it works pretty good for this case too. So just stick with it. Okay, and then we send it out, and that's it. Oh, wait, we got to do our DC filter, of course. Xn is equal to, what's it called? DC filters. Yeah. Channel. Process sample. Channel. Xn, our input. Let's get rid of this warning. We're going to say static cast to int. All right, so I'm going to build this standalone real quick just to make sure it doesn't like crash. Oh, and then we got to actually put it in our process block. That's the other thing. tube float mtube. That's good enough. Then we prepare it, process, and we just pass it the block, which is upsampled block, and num oversampled samples. Oh, I must have missed one in here. Oh yeah, I did. Okay, so xnk, which I'm putting as 1, thresh, which needs to be 1.5, just like the other one, and then that offset. Okay, so that's the one we're missing. All right, I'm gonna build again, standalone, just to make sure it doesn't blow up. Okay, there we go. Should be good. Build it AU. That certainly doesn't look great. I blew it. All right, what did I do wrong? Oh, yeah, that's what it was. Thanks for that. Good looking out. Let's just initialize it. Dot set current and target value to 1. Oh, did I did I not uncomment out stuff? Yeah, of course. Ooh, there we go. This is looking correct. Okay, there we go. We got that little bit of sway in the bottom, and then we've got our DC filter. Yep. Okay, let's see. Think we're gonna be good. Let's see. Yep, and we got that slight bump. Yeah, there we go. Oh, that's kind of weird looking right there though. Let's we got to scale it back while we're driving it. So we could just do xn times 1 divided by drive, which isn't, you know, a super efficient way, but if that fixes it, let's implement that a little bit better. That way, as we turn the drive up, the overall volume will come down equal to drive. Yeah, there we go. Oh, but it's still happening. Okay, I thought that there's some kind of threshold happening right here, and I think maybe that could be a mistake in the code because I don't remember that being a thing. So let's just go over it real quick. Or if the clip point positive is greater than 1. Then we do this. Oh, I must have missed this also. That should be it. There we go. So let's play it in Logic real quick. View toward DSP, the comet strip. All right. I set the DC filter cutoffs to 5 instead of 10. That might make a difference. I also set the drive to 2, and then I've got the shift at 1. Yeah, that looks a little better. I think that's better. Low pass filter, because that will probably help smooth it out a bit. The Miller cap, which was it's some kind of capacitor that does a low pass at 10,000 hertz. So sure, I'm just gonna call it the Miller cap filter. I'm just gonna copy and paste this. Filter. Miller cap filter. This is gonna be a low pass, and this is gonna be at 10K. And then we do the same thing. Miller cap filter. All right, let's try that. Okay, I mean, it sounds good. The other thing we can do is we can check the performance, and this is a debug build, so it's not the best way to check, but looks like it takes about 6 milliseconds for our process block to run. And we can do one small optimization here. We can get rid of this if statement, and we can do, so we do a mask pattern. Let's see, const float, or it's going to give us a warning. We'll do auto. We'll call it mask is equal to static cast to float, and that is xn greater than 0. We could do greater than equal to 0, I think. Probably be fine. So we have this mask, and we know that if it's positive, we do this, and if not, we do this. So we can actually just use the mix kind of logic. So if we do 1 minus mask times our dry, which would be not really our dry, it's the thing we want when our mask is negative, which I think is xn. And then we add the thing that we want when the mask is positive, which is this. And I think that's good. And mask is only ever going to be 0 or 1, so we don't have to worry about an actual like mix, like in between values or anything. So that's a tiny little optimization. Now I did it for this entire block earlier, and it actually made it slower because there was so much more math going on, because there's like 4 to 6 if statements that you have to mask for. Let's just make sure this actually works. Still seems fine. Okay. So yeah, cool. Thanks for watching. I will see y'all next time.